Hi friends, welcome back. Now let us see how the problem of contiguous memory allocation, that is the fragmentation problem, can be avoided through predefining the segments of the memory and assign them as and when required. And this predefined size of memory is called a page. So the process is called paging. So let's look at what a paging is and how it's done. So paging is a process of breaking physical memory into fixed size blocks called frames. So the memory, that is a physical memory, is divided into fixed size blocks, and each block is called a frame. On the other side, the logical memory of any process is also divided into blocks of the same size, and these blocks are called pages. And the whole process of paging is to accommodate the pages onto the main memory and make the things work. So here the pages are loaded into any available memory frame from their source. Backing store is divided into fixed size blocks that are of same size as the memory frames. The paging is a process that permits the physical address space process to be a non-contiguous one, so need not be contiguous memory to be associated with any process. So a process can be split up into multiple pages, and each page can be accommodated in some physical frame, and these frames need not be contiguous in the memory. So this avoids the external fragmentation problem, and also the need for compaction also is avoided here. So this figure talks about how the whole thing happens. The CPU works only with the logical address, and the logical address consists of two things. One is the logical page number P, and in that P where exactly our instruction is, that is D. So P and D are the two things. The P refers to page number, and there is some page table which maps the page of the process to a particular frame in the physical memory. So what we say is a page, so that is the index in the page table. P is the index in the page table, and D is the index inside the page. So we have some page, and we go to that index onto the page table, and that says the whole page is located at some frame F, and we go to that frame F, and the displacement D is same in the same case also, and that tells that this is a particular frame which we are looking for, and this is the page what we were looking for, and that much is the displacement we have. So this page is actually dumped here, and for dumping this we make use of this page table and the displacement and so on. So that's logic of paging. So let's take an example of a process. A process is consisting of four pages: page 0, page 1, page 2, and page 3, so which we call logical memory. And we do have a page table, and then we have location or frame number 1 is free, so we have allotted frame number 1 for page 0. So this page 0 gets to the index 0 of the page table, and here we have the frame number says is 1. So page 0 goes, so this page 0 we have to look into page table where exactly it is located in the main memory. It says that it is located in page 1, so we have page 1, frame 1, occupying the page 0. Same way, page 1, if you look at it, it is available on page 4. Yes, page 1 is at frame 4, and therefore this page table is saying, so page 1 is in frame 4, go here. So you are talking about this process, and this process try to say that there is some jump from here to here. Then it says where exactly to jump. So first thing is itself go to page 0 and so much of the displacement, that is the location where to jump, and that page number and the location or the displacement is given, and says page 0. Page 0 means look at where is it. It is in frame 1. So go to frame 1, and frame 1 starts here. So from here have that displacement, and that's the location where we have to jump. So we had jumped from here to here. So that's what we were trying to say that. Same way, page 2 we have page 3 is there at frame 7, and so on. So the next thing it says is another example where we have a page of size 4. So there is a page of 4 bytes, and totally 1 2 3 4 bytes of data we have, and we wanted to store into the physical memory, and it says that page 0 goes into frame 5. Yeah, page 0, this is page 0 goes to frame 5. So this ABCD goes to ABCD here. Same way EFGH goes to frame 6. HIJK, IJKL goes here, and MNOP goes here. So how do we calculate that? Is we have, this is a page 0. Then if you are talking about the data B, then the index is 1 in this. Page is 0, index is 1, so 0, so that says go to 5, and 5 is located at this. So how do we get to 5? Because we know that each one has 4 bytes to write. Therefore 0 will be at 0, 1 will be at 4, 2 will be at 8, 3 will be at 16, and so on. That means it is something to do with 4 into P plus D. So we are talking about P equal to 0, therefore 4 into P, 4 into this F. What is F talking about? F is talking about 5. So this is 4 into 5 plus what is P? B is having displacement of 1. So this is 21. So A is 20, B is 21, and so on. So that way we can accommodate the things. So you can take this example. A is at page 0, frame is 5, so P is equal to 5, D equal to 0, so location is 20. So another example for G, if you look at G is there at page 1, that means page 1 means frame 6, so P is equal to 6, and G is at location 0, 1, 2, so displacement is 2, so therefore 6 into 4 plus 2 is 26, so G is, this is 24, 25, 26, so this is 26. So that's how we can get it. So we can just look at how the whole process happens, how the allocation process happens. So we have a set of frames which are free, and we have pages of a new process, so 4 pages are there, and as of now these are the frames which are free. So we keep allotting one by one. So page 0 goes to frame 14, page 0 goes to frame 14, page 1 go to frame 13, page 2 goes to frame 18, and page 3 goes to frame 20. So we have 0 at frame 14, at 14 we have page 0, at 13 we have page 1, at 18 we have page 2, and at 20 we have page 3, and applying the same logic. So P into the size of page plus displacement will provide the exact location of any element in the page we are looking for. So that's what we just discussed. So how does this whole hardware support is there? So we have a CPU which gives out the logical address P and D, and first thing is it looks at the page number. So if you find the page number where we are looking at TLB. TLB is translation look ahead buffer. So if we have already selected that page earlier and we have dumped onto the some frame earlier, then we have that in this thing, that is which page number is available at which frame. So if the page number you are looking for, if it is available in this table, then we say that we have hit it. That means we have that particular page already on the physical memory. So we can just select the page number corresponding frame number and take that frame number, take the displacement that gives us physical address, directly jump there. So that is one option. And if that page does not exist, then go down and see that the page table and where exactly is situated. So that is what we get again. So this path is what we already discussed. This one is a new one which talks about the translation look ahead buffer. That means if the same things are being used again and again and again, then we can create a small list that are used quite often. So this small list is first searched, so the searching time is less compared to a big table which needs a long search. So a small table that talks about frequently used pages, and those frequently used pages should be put in some frame, so that in future if any replacement is required, so if you want a free frame, then one of the pages from that frame has to be removed, and the question comes is which one to be removed. So better avoid removing the pages which are from here, so that because these are quite commonly used, most oftenly used, so this maybe required some more time. So some of things which are not here but they are here can be replaced. So some frame which is no longer used can be replaced and work with that. So that's about paging. So keep watching. Thank you.